So WebAssembly is a very much work in progress. And what we're trying to do is we're trying to make native code run on the web just like it was any other kind of web content. Safe, secure, and hopefully a bit of a performance advantage over JavaScript in some cases. Our ultimate goal is to make this a standard, and our ultimate goal is to make sure that all of the browsers have native implementations in them. So we're working with a bunch of other people right now. So this is not our work in the sense that just Google. This is a number of people contributing. I'm really optimistic about this because the major browser vendors are talking. You know, this is not commitment, nothing for sure, but people are talking, people are interested. And this is potentially going to be the first technology for running native code on the web that is both cross-browser and supports shared memory concurrency. And with both those, there's a chance that this is going to have a very interesting impact on the web. So native code on the web. A lot of you probably haven't dealt with it because you're focused on the document side of things, the JavaScript side of things. What are people using native code on the web to do now? A early adopter for this is game engines. So we have Epic and, sorry, trying to find a place that I'm not getting as much feedback. Early adopters such as Epic and Unity have taken their game engines which run on mobile devices, for example. And in the past, they ran, like Unity ran on NPAPI, that went away. And now they're looking for other opportunities to make their games also run on the web. So in some ways, it's radical cross-platform development. You run on desktops, you run on mobile, and you can run on the web if you can make native code actually run on the web. Otherwise, it's too much porting work. Other people doing this is there's a lot of legacy programs like emulators, so DOSBox, JS Linux. Someone actually booted Linux in a web browser. And this is an example of how you can take existing native code and through being insane and spending a lot of work, you can make it work. But the question is, how can we lower this bar so you don't require extremely intelligent, high-paid, insane people spending lots of time to make it work? You know, right now it's possible, but how do we make it so your average developer can actually use native code as part of their web applications? Another thread I particularly like here is the idea of the extensible web. We have lots of high-level APIs. How do we expose more low-level APIs? How do we make it so we can define the web as web content? There is an interesting website called Replit where you can do things like run Python in your web page. And this is based around compiling native code to JavaScript. It runs in a pane. And it sort of works for many things. You can just run an interactive loop. People have cross-compiled PDF viewers to JavaScript. And there's been some experiences with media decoding. Imagine a world where things like video codecs don't have to be built into the browser. They are, in fact, something that could be shipped across the wire and would be safe to run, but at the same time, give you nearly the full performance of have something running directly on the hardware. But it ain't all wine and roses. The web and native are two very different platforms. The web came from the idea that it's just a document. And we've sort of taken this in some ways to ridiculous extremes, but resulted in a very interesting platform that's safe, that's portable, that's ephemeral. And native apps live in a different world that don't have those nice properties, but they have other behavior. So one of the big porting problems with going from native to the web is that the web is asynchronous. So a lot of native programs demand synchronous interfaces. You know, I want to use fopen. So you no longer can synchronously get a result from fopen or fread. So how do you port your program? And you end up having to do awful things like slice your entire stack. So you unwind it, then wait for the callback, and then resume from wherever you are. So the amount of refactoring and program transformation you have to take a program that expects synchronous APIs and make it run in an environment that only provides asynchronous APIs is a whole lot of work. A related problem is that there's no threads or shared state. Now, many people say threads, boo, hiss, they're hard to use. If you're using threads, you're using it wrong. But ultimately, a lot of the pieces of software that you're using are built on top of threads. They're a very low-level primitive which can do things like give you reliable behavior. You have to worry less about jank if you have a background thread for doing audio. And things like that. So a lot of the structure of our existing native code is built on top of threads, and if you don't have those, you can't use the existing structure. Another issue is inconsistent performance, is we've gotten JavaScript to run very well, but there's still just weird pitfalls here and there. There's GC jank. There's cases where the JavaScript engine says, well, you know, I don't know how to deal with this right now, so I'm just going to run slower. So when you're like trying to really push the limits and do something that crunches a lot of numbers, you get some really weird behavior. And I'll show a bit of this when I do a demo later. So bottom line is right now, running native code on the web is not fun. There's a lot of people who want to do it, but it's a high barrier to entry. So we've been trying for a while, almost from the advent of the web. Originally, it was documents. Then we figured, ooh, interactive documents, and we got JavaScript. And then people said, well, what about other kinds of documents? What about PDFs, vector graphics? And this is where NPI came from, is we just burned a hole straight through the browser and added more functionality to it. And after a while, we realized this was a bad idea from the security perspective, et cetera, et cetera. And kind of in this story, the top of this is the plugin era. And especially as we went to mobile, we decided not to support plugins. So you can't really consider plugins to be part of the web platform. In the right column, there's the issue of shared memory and cross-browser. So there's been no technology that has both. So there's been attempts to do something other than JavaScript, like native client. And this ended up being a Chrome-only technology. Whereas you have things like mscript and asm.js, which says, hey, we'll compile the JavaScript. But ultimately, you had to work within the limitations of JavaScript. You had to relinquish control to the event loop. You had to remove all the threads from your program. So WebAssembly is hopefully where we hit all the points, where it works like web content, it works in all web browser, and you get shared memory multi-threading. How does it work? The answer, in some ways, is surprisingly dull. It's just a piece of web content. Is you have, you know, a render process is what amounts to. You load in HTML, JavaScript, data like image files, and now you just load in a WebAssembly binary. And sort of like JavaScript, it has its VM for the source code, is WebAssembly also has a VM for its source code, and it integrates as part of your web app. And this binary is designed to be generated by compilers. So it's assumed that there's some C compiler out there which will suck in C source files and output the WebAssembly binary. But really, any compiler could target this as far as we're concerned. But you know, for now, let's just talk about C source code. But I lied to you, is there really isn't a separate VM for WebAssembly, at least as things are currently being implemented. Everyone who's thinking about this is retasking the JavaScript engine, because they're looking for a tight integration between JavaScript and WebAssembly. You know, WebAssembly can call JavaScript and vice versa, and really they have similar needs, such as generate machine instructions. So because you already have all this infrastructure for generating machine instructions in the JavaScript backend, why not just use this for WebAssembly too? And what happens is that the binary essentially goes in at a lower level. It's a typed binary instead of the dynamically typed, let's execute it for a while to figure out what the types actually are, nature of JavaScript. So you can hit the ground running faster. What's actually in the file? Well, it's a binary blob. So this is kind of a hand-wavy visualization of what's actually going on. Is if you had an expression like in the upper left corner, is you're doing a function call, and then you're adding two things together, and there's two local variables. In JavaScript, you look at that and say, well, that's a call, and there's expressions. I don't know the types. In WebAssembly, we're being a little more explicit about what each of the nodes are. Each of the nodes will have the return type either directly declared or inferable. So for example, because we're calling foo, we know the return type of foo. Or there's an int32 add, we know it's going to be int32. We never have to worry about, well, what if we're adding strings together? Oh, then it will return a string. Can't happen. It's strictly typed. The fact it's a binary format is actually pretty important because it gets us smaller. The disk footprint is smaller. It's, I think it's about a third the size on disk. But of course, there's some entropy, entropy preservation thing going on, is that when you actually run a compressor over it, you lose some of the advantage over the text format, because the text compresses really well compared to binary. But it still looks like there is about a 25% edge, is if you take an equivalent program, the binary encoded version, after compression is about 25% smaller. And that pays all sorts of dividends about loading faster, things like that. The most interesting thing, though, is that parsing binary is blazingly fast. It's designed for a machine to read unlike text. So in terms of just parsing the file, it's about 23 times faster. Now, we're doing all sorts of tricks right now to amortize parsing speed for JavaScript, like doing it while we download it. This doesn't work as well as a cold load and things like that, and I think there's been some tracing in the field that shows that JavaScript parsing is actually a non-insignificant part of page execution time and page load time out in the field. So that's describing the format. What's actually going on semantically? And when I first did this diagram, I realized it's very boring. Normally when we're talking about languages, we're talking about objects, we're talking about strings and things along those lines. But with WebAssembly, you just get a big chunk of memory. When you start up, you say, hey, give me like 128 megs of memory or something like that. And it gives you what amounts to an address space, which you can allocate bytes in it. You can pull numbers out of it, do math on numbers, store them back. So this isn't a programming language as we traditionally think about it. It's a portable machine model. We're providing you loads and stores, we're providing you memory, we're providing you arithmetic operations. The trick here, though, is that you have a constrained sandbox that you can actually access in terms of memory. Like you get 128 megs or 512, whatever you wish. And all your loads and stores have to be in that range. So there's an implicit bounds check every time you do a load and store. And this is effectively what makes you safe, is you can't clobber memory elsewhere in the render process. So having a bunch of code that can do math and manipulate memory and can't touch anything else, that's pretty boring. So you take it up a step by saying that you can call in and out of WebAssembly and JavaScript. And you can call in both directions synchronously. So this is similar if you're familiar with JNI or have done any Python programming, is inter-language interoperability. So you have to declare the interface. You have to say, what are all my imports? What are all my exports? What are the types? And then your C program, of course, can link to these. And your JavaScript program, when it instantiates a WASM module, sees a bunch of functions on it, which can call just like they were JavaScript functions. Question?
Yes, in that example, you declared the bar function as returning an int. And so that is then, like, do you have to hand on hard as programmer in JavaScript, it could return anything?
Yes.
And so you just have to hand on hard say, trust me, that really is an int?
Well, you can trust but verify. So you're sort of saying that this program should return an int, and if it doesn't, I'm going to fault and take everything down. Gotcha. So, I mean, we could do something stupid like coerce it to 0, but I think right now it's just going to be a hard error if type signatures don't match. So this is where the interesting thing comes in, is it's pretty much impossible to do big bang on the web. Instead, you have to be sneaky and find ways to embarrass other people until they adopt your technology. Or at least get your technology to run everywhere and run it well. Somewhat cynically, I call this embarrassment-driven development. But it works. This sort of sums how the web works, is that you get something that's compelling, you get something that's fast, you get something that people want, and you also have it run on their system just a little slower until it works. So with WebAssembly, this is what we're planning for, is in the first generation, the WebAssembly files are going to be translatable to JavaScript. And it's going to be essentially equivalent to ASM.js, as you can statically or dynamically, just in time, translate your binary into JavaScript, which can run in browsers without native support. Downside, of course, is it takes a little longer to load, and it won't have as consistent of performance as having, just going directly into the back end. You'll have to go through JavaScript, and it'll parse slower, things like that. Which brings us to the demo. This is a patched version of Chrome and a bit of a assembler, so to speak, that I whipped up. This is not official assembly language in any way, shape, or form. It's just a tool. So this is drawing a ray-traced sphere. And right now it's running entirely in JavaScript. And you can kind of see there's code, there's square roots, there's loads, there's stores. And if you look up in the upper right-hand corner, it's running about 33 frames a second. Now, I'm going to do something that's totally unfair. And I apologize to anyone who works on JavaScript engines here. I am cheating, and they know I'm cheating, and I'll explain it in a moment. So if I flip to the native WASM backend running inside Chrome, you'll see the frames a second go from 30 to, about 80. And wow, WebAssembly wins, right? We're over twice as fast. Okay, but I was cheating. I had to say that. So what's going on here is that this example is using a lot of float32 math. So instead of using float64, it's saying, oh, let me do a 32-bit square root, things along those lines. So when you actually generate the JavaScript out of this, it does a lot of bouncing back and forth between 32 and 64. So it'll, for example, use math.squareroot, which gives you a 64-bit result, then immediately do a math.fround to go back to 32-bit precision. Now, if the JavaScript engine cared, or more correctly, if we had the man hours to throw at it, it could recognize this pattern and just do all the 32-bit operations directly. But it doesn't. But when we give it to WebAssembly, because we type everything as float32, it sees from the beginning, oh, I can just do 32-bit math all the way. So there is no reason that JavaScript could not be running as fast as WebAssembly for this example, given sufficient time and effort to optimize for 32-bit math. And then there may be problems after that. So in some ways, the value of WebAssembly is that it's just simpler to run fast, because you have more of the information up front. You don't have to do any clever pattern matching. You don't have to do runtime type inference. You just know what's going on. Now, here's another fun thing, is I sometimes can do this, sometimes can't. Again, abusing the JavaScript engines in ways it shouldn't be. Is I'm flipping back to normal JavaScript. It's running about 33 frames a second. Back to WebAssembly, 80 frames a second. Back to native JavaScript, 25 frames a second. So we lost some performance in there. And what I was doing is I was essentially spamming the same JavaScript context with more and more code. Every time I flip back and forth, I'm regenerating all the JavaScript. So at some point, V8 was like, wow, I've already compiled a lot of code. You're still giving me a lot of code. I'm not going to try as hard to optimize anymore. And it was just some heuristic. There's probably some web page out there that spams it with too much code, so it has to spend less time compiling. So on average, this works. But for this corner case, I was able to degrade performance by doing something unnatural, as it were. But of course, if we go back to WebAssembly, missed my click, there's no real heuristics about over time. It's an entirely new instance. So that would be the demo. Present. So here's a rough roadmap of what we're hoping for, planning on. All of these numbers are fake. I just threw them out there and no one laughed at me too much, but it's better than nothing. So hopefully sometime next year we're going to have native support for single-threaded WebAssembly. And in some ways this will be a binary equivalent of something along the lines of WASM.js. It'll load faster and it'll run faster than if it's a textual format. Now, threads are very, very important for supporting native code. So I just backtracked on that. I said for version 1 we aren't going to have it. But as it turns out, specifying threads is very complicated. It's sort of the graveyard of empires, is when you start talking about, oh, let's do a memory model. So just from the strategic perspective, we have decided that as soon as possible, we will add threads to it. But for version 1, we are not coupling it with threads and just trying to set up for it. So in practice, we're probably going to have threads completely implemented by the time version 1 releases. But we're not going to step in that bear trap yet. So beyond that, there's a lot of other stuff we need to add. Notable stuff, including single instruction, multiple data, is that can save potentially a lot of battery life on mobile. Dynamic linking is one of the issues you're going to run into with native code, especially when you link everything together and optimize it, is that's a big chunk of data. And right now, as things work, you'll probably have to re-download it every time it changes. So as soon as you start having dynamic linking, you can start sharing code between websites. You can have partial re-downloads, things that are very important for the web. And APIs, is we're going to need some sort of API support from the browser. And I will get into that in the next section. So things that keep me up at night. So this is the section of all of the design complexities I see. And I'm naturally a worrier. And these are all the things that worry me. I don't want you to get a distorted view, oh, everything's doomed. I'm sort of laying this out there to try to get help. A lot of these things come down to browser integration. And this is who I'm talking to. So I really want to get this idea in your mind, these are the things we are thinking about. These are the problems we're going to be facing. And anything you could do to help us think through this, work through this, figure out what the infrastructure is for this, would be really appreciated. So do not freak out. This is not something where next year it's like, all of these things are coming due. But probably over the next 5 years, these are things that, if we succeed, they will become relevant issues, and we want to figure out how to do it. And part of the thing that we have to figure out with all of these is how to incrementally evolve, how to figure out what the small steps are so we can get the web platform heading in the direction that can actually make this work. So portable native code. This is a non-issue. We've been working on this for a while. The native client team has been thinking about portable native code in a way all of the JavaScript people have been thinking about portable native code, is how to take something that's portable and make it run as fast as possible on your machine and start up. So really, it all comes down to how we integrate with the browser. These are the things that really need some thinking about. So the big one is the mismatch between synchronous and asynchronous programming models. The web is very much asynchronous. And if you want to have good support of native code, you have to support blocking. You have to support synchronous action. So here's a rough sketch of what a threaded WASM program would look like. We want to be able to call in and out from JavaScript to WebAssembly. And on some level, this means you're effectively sharing a stack, because you can't unwind one stack without unwinding the other. So there's going to be some stack there which is going to have mixed JavaScript and WebAssembly. And because it's going to be because it's mixing with the JavaScript, it's essentially going to run on the main thread somewhere, like the main thread of a web page. So there will be a main thread that has WebAssembly and JavaScript code running on it. And if you ever want to get a callback from the browser, you have to unwind the entire stack, including WebAssembly. So this isn't ideal for porting native code, but it's necessary for interoperating with the browser. Now, the fun question comes is, how do you interact with other threads? So other threads interacting with you is fairly straightforward. Say you have a non-main thread WebAssembly thread. Well, it can send a post message to the main thread. It can queue up something in your event loop. Now, this isn't ideal. There's some latency issues. So in the worst case, you have to wake up the main thread. And that's going to be a relatively expensive operation. So benchmarking, you're going to be spending maybe 1/4 of a millisecond, roughly in there, to do a one-direction post message. If you're doing round trip, in the past, I found it's about 1/2 a millisecond. And it's consistent between the browsers that I've tested. So I'm coming to believe that this is just thread wake-up cost, but I haven't fully verified that. And there's a maximum amount of turns, as you can really only get about 40,000 of these events a second on a high-end system. So there's some limitation in your communication over post message. Now, problems get a little weirder because the WASM threads don't have event loops. Or maybe they will. We'll get to that option later. But start from the position they don't have event loops. So to communicate backwards, back to the thread, the main thread would have to do it through shared memory. It'd have to use some sort of atomics operation or some sort of futex operation to signal, hey, background thread, here's the result to what you want. But then the question is, on the main thread, can you do things like futex wait? Can you block the main thread waiting for one of the background threads to communicate to you? If it's allowed, it's probably not advised. So figuring out how to structure the communication so the main thread can potentially multiplex between things it's waiting on. It needs to either wait on the event loop or wait on a futex. How do you do that? It's a little unclear at this point. And there's also issues with deadlocking. If the background thread delegates to the main thread, then the main thread delegates to the background thread. You've essentially deadlocked yourself. And normally how you deal with this is you have reentrant event loop pumping or something like that, which is totally not supported on the web platform. And another thing here is, how do the background threads get access to APIs? Right now the only obvious plan is to delegate or thunk through the main thread and then have the main thread delegate to the existing APIs. So how do we move beyond that? OK, so what if we just give the background thread an event loop? As a bonus, let's also give it a JS context. And let's say call it a web worker, just pulling that name out of nowhere. So if we say that a WebAssembly thread is equivalent to a web worker, this solves some of the problems in the fact that you can post message back to it. Some of the problems in the fact that you can have other JavaScript objects in there. But things still are not the most useful, because in this background thread, if you really want to support native code, you potentially have to run forever. and you're not going to be returning to the event loop. If you don't return to the event loop, you can't get any more messages in. So you can sort of use the APIs, but as soon as you go off on your own, you get punished, and the system stops talking to you. And you can only send post messages and see things coming in through your main memory. Another issue is that you'd have an entirely separate JavaScript context. So what happens if on one thread you want to open a file? Well, you can emulate it in terms of JavaScript by doing some sort of data source acquisition, and you have an object living in your JavaScript context. But then you want to pass the file handle to another thread. Well, your JavaScript object lives in the wrong place now. So then you have to have some sort of proxying, or you have to move it over. But if that other thread isn't returning to its event loop, you can't even post message it. So how you'd actually deal with separate JavaScript contexts and provide a coherent and useful native API, again, is one of these very hard problems I'm not sure is solvable. Another thing is, as soon as you start having different JavaScript contexts, at some point in WebAssembly, we're going to have to stop all the threads. Well, which threads do you stop? All of the threads in the render process, all of the workers, whether or not they've touched WebAssembly? Eesh. So scoping, that's a little difficult. Other fun things that keep me up at night is, what about memory? So one of the things we want for WebAssembly is that it provides a competitive experience to native mobile. We got native code, we have it running in your web browser. Why not do this instead of writing a native mobile app? One of the things that seems like it's going to be a little sketchy is memory usage. So if you look at what's going on inside a browser, you have the OS, you have the browser, you have web content, you have JavaScript, and you have WebAssembly, all sort of sitting, as infrastructure just to make the application run. And native mobile apps are going to have a little less memory pressure because they have fewer layers, and they can get closer to the metal. The big issue, though, is that WebAssembly requires allocating a contiguous chunk of memory for your application's address space. I said earlier you can get 128 or 512 megabytes of memory. Well, that has to be one allocation, so you can access it with exactly one bounds check. So on 32-bit devices, when you have the OS and the browser and the web content and the JavaScript and the WebAssembly, possibly more than one module running all in the same address space, how do you do that large contiguous allocation? So figuring out how we live on 32-bit devices, figuring out what sort of things we have to do in Chrome to free up address space, that's really important. There's the belief that we can start with smaller address spaces, then enlarge them as we go. And again, will this be possible on 32-bit address spaces with fragmentation? Physical memory limits is, at one point, does all the other stuff occupy too much physical memory? How much physical memory can we get versus a 32-bit native application? So in terms of address space allocation, like 32-bit mobile devices with a fairly clean process, we can get about 256 megs of memory max. And on 64-bit devices, we were getting about 512 max. So figuring out exactly where these limits come and how to get past them is one thing we need to look at. Exposing memory is, in the old WASM.js days, memory is just an array buffer, which is a flat linear series of bytes. But when you actually look at real native platforms, you start blowing holes in it. For example, the page around 0 is not mapped, so when you dereference a null pointer, you actually get a fault. You don't in WASM.js. You just get whatever data was at 0. It's kind of annoying to debug. But so in the future, what happens if we can unmap pages? What happens if we could, say, mmap files into memory, which we'll get into in a moment? This means that WASM memory is not, in fact, just a flat buffer of memory. And people who look at it cannot assume it is. So, and it potentially could move, like we talked about reallocating. So from the JavaScript point of view, if you try to pretend it's an array buffer, you could potentially have faults if you try to poke in the middle of it. Or there could be concurrency issues where it tries to move as you access it due to action of a background thread. How do you prevent that from happening? So the semantics and implementation of the WASM address space is going to be distinctly different from an array buffer. And when you pass it into the browser, say you want to upload a texture from WASM's address space, well, OK, it's all there. Let me read it. Oops, someone unmapped the middle of it while I was trying to read it. The browser crashes. We obviously want to prevent this. So on some level, the browser is going to need to be aware and take a lock on WASM's address space before it actually starts reading. And that lock will validate, yes, this is a contiguous region. No, you will not crash when you access it. This is not as important, but native code tends to be a little on the big side. And there's probably going to need to be mitigations we do, like differential updates. is you're going to say, hey, I have this version of the file. Give me the patch to get up to the current version. Things along those lines. We're going to need to cache the compiled code, which means that the same file is going to be stored multiple times on disk. So when you start thinking about cache eviction, if you evict the source file for that, then you probably also want to evict the compiled copy, and things along those lines. So the caching heuristics, what gets evicted, when it gets evicted, much more complicated than it is when you don't have this multi-stage caching. And the big one here is APIs. So first version is all we have is FFI. Is we FFI out to JavaScript, and then JavaScript implements the APIs to us. But this is a fairly unsatisfying solution if we're talking about something we want to be a first-class citizen of the web platform. So everyone wants to use web APIs, as we spent a lot of time defining various APIs for the web, audio, WebGL, things like that. And they have security models embedded in them. We want exactly the same security. We want the same behavior. We don't want to spend a lot of time re-specifying things. But the devil's in the details. So the question is, how do we do that? And I'll look at it in the next few slides. They need to be thread safe. So if you open a file on one thread, or you open a stream of data from the network on one thread, can you also continue reading it from another thread? Or are you permanently locked to that thread? From a user point of view, we want APIs to be able to migrate between threads, except for cases like WebGL, where for performance, Web Affinity is fine. We want things to be zero copy. So we want to be able to directly use things in WASM's address space. And like M mapping, like currently you just have array buffers, whereas we want to plop things down in the address space. So for example, we could decode a PNG file directly into a canvas. And in order to do that, the canvas area would need to be located in WASM's address space. What about blocking APIs? And ultimately, none of these APIs should require the presence of garbage collection just to eliminate jank. So they're essentially reference counted. So one of the ideas is, why don't we just use WebIDL? WebIDL is language neutral, right? Well, no, it really isn't. WebIDL is very much specific to JavaScript in a lot of ways. So for example, WebIDL and a lot of the interfaces defined with it take advantage of any. So previously for OpenGL, there was like get parameter f, get parameter I. And they would return different types, like floating point or integer. Well, this is JavaScript, right? So why don't we just return whatever type we want to? Which works fine for JavaScript, but then you say, what's the native binding for this? And really, ideally, we'd want something similar to the original WebGL API that did not have a polymorphic return type. If you look at things like constants, they're defined as members of an object, whereas in native code, they should just be constants in a file somewhere. And actually, saying, oh, I have this opaque object, which is a context, let me access the field, which is a constant that I know all the time, that's not how you'd want to do native programming. Image data is particularly interesting because it shows like there's ABI stability issues. It's like the order of fields is not guaranteed. If you inherit from something, that could add a field. That would shift all your fields down. So you can't actually treat any of these objects as if they are structures. You have to treat them as opaque handles. And you'll also see that the image data has an associated buffer with it. It has this data thing. So the system says, hey, when you have an image data, here's a chunk of memory for you to use. And it's doing this for implementation reasons, like there's shared memory. And it wants to make sure that you always are using shared memory with the image data so it gets to the browser process as fast as possible. But how do you make this part of WASM's address space? It's a separate buffer. So when you're doing loads and stores, you can only go into the address space. So if you have to go to the buffer, you can no longer use loads and stores. So it's a little complicated. Callbacks. Another fun thing is a lot of them have any return types, which basically means the system does not care. It just ignores whatever your callback returns. But when you ask how does this translate to a static type system, you'd probably want that to be void or something like that. You don't want the actual return type to be any. And the question is, how does this interact with event loops? What's the lifetime of the callback? Some callbacks can be invoked multiple times. Some can be invoked once. If you know it can only be invoked once, you might be able to transform it into a synchronous call, things along those lines. So WebIDL is sort of in the area, but looking at it right now, it seems like there need to be lots of edits to existing interfaces to make them do what we need. So which leads to the question, which I don't think we've answered very well yet, is how do we do this incrementally? How do we get high-performance web APIs for native code without having to do massive amounts of work. And I'll throw that out and see if anyone has any answers after this. So from 5 years from now, if WASM succeeds, the way we hope it does, there's going to be threading and blocking issues. Asynchronous versus synchronous barriers. Like binding generation. Right now we're generating bindings for JavaScript. We probably want to generate bindings for WebAssembly. There's going to be larger content, native executables, things along those lines. And potentially, this will push us farther into the extensible web, is that components of the browser can be shifted towards content. And that would be a huge one. So I burned through that really fast. Questions? Yo.
You mentioned mobile. Are you planning to ship on mobile?
We mentioned mobile. Are we planning to ship on mobile? Yes.
Great.
That is what we call cross-browser. So if it doesn't run on mobile, that is not cross-browser, and that is not a web technology. In fact, at least from my point of view, that's the most interesting platform because it provides the hardest constraints on performance, on memory, and things like that. And I think we need to do there well. So we were talking about 32 versus 64, and it's like, well, what do we do on 32? Well, by the time this is ready, will 32-bit mobile be a thing? And if you sit down and squint on it and draw lines through like Unity's numbers of their user base and just do a linear extrapolation, probably 5 years from now, about 50% of the user base will be 32-bit, unless there's some sort of phase change, which we can hope for, but if current trends sustain, we will have to deal with it. What?
Does that include WebView? Does mobile include WebView?
Does mobile include WebView? Haven't thought about it that much. I mean, but we want native code on the web to be competitive with native apps. So probably whatever that takes.
The discussion of shared memory was really interesting. I'm particularly nervous about the idea of letting the main thread block on the locks,
Yes.
Because then the developers have to, in order to reason about the responsiveness of their main thread, they have to be able to reason about the responsiveness of everything that might take a lock, and that's
Yes.
really hard, right? But a bunch of that design seems to be predicated on the idea that post message is incurably slow. And you said that you thought it was just thread wake-up cost, right? I've got data, like, for example, when we're scrolling, we hop like 5 or 6 threads per frame, and it's never shown up. I just did a quick check on my laptop, and it was like 10 microseconds to wake up, to hop between threads.
It depends on a lot of factors, including like how hot things are. So if you aren't going to sleep, going to sleep doesn't matter.
But if thread wake-up cost is a problem, we've got a much bigger problem.
Right.
Like it would be a huge problem for scrolling, for example.
But there's also the issue of like latency versus throughput. So the fact your thread's asleep lets other threads run. So it's just the amount of time it takes to wake it up, maybe the limiting factor if you have to do round trips. So it isn't entirely clear what's going on, but I have consistently found that delegating to the main loop has a non-zero latency cost. And roughly speaking, burning the numbers down, it's about 1 million cycles. So not the end of the world.
Seems like it's worth pushing on that further. Like if we could figure out how to like, because if you can post message transferable to at least get your data over to the workers, and then all the workers can have shared memory with each other. Like that's totally cool.
Yeah, but like ultimately you are going to want your threads to have the illusion of synchronous APIs. So when I am in this background thread and I want to read from a file, I want to request the read, and then when that request returns, I want to have the data in front of me.
And you want to do that from the JavaScript main thread? Or it's okay to just do that from your worker thread?
Right now, let's just say from the background thread. Call the worker if you want, call the pure WASM thread if you want. You have to have some way to do that. And in the worst case, we have to be able to delegate to the main thread. So there has to be some way on the background thread that you can delegate to the main thread. It responds and sends a response. Now that's sort of like the minimum thing there. And making post message faster would help that. But right now I'm sort of assuming that we have to pay that cost no matter what, because the main thread will be returning to the event loop. And the only way to activate it is by activating the event loop by doing a post message to it. And then the reply, because the recipient may not have an event loop, has to be through shared memory. Now, you said it's kind of tricky to reason about blocking and things like that, and the answer is yes. But I don't think you can get around it. So for example, there's the Futex API, which basically says, hey, I want to sleep until someone wakes me up, or wake up this person. And this is usually coupled with atomics, so it's purely an efficiency thing. Is you're saying, well, instead of doing a spin lock, I'm going to cooperate and go to sleep. Now, if you take the Futex API away, you can just do a spin lock. So as long as the main thread can access the shared memory in any way, shape, or form with a synchronizing primitive such as atomics, a badly behaved program can do arbitrarily bad things. But of course, you can do this even when you don't have concurrency. Is you can have infinite loops and things like that. And the browser just has to be aware enough of when to wake them up or when to kill them or what's sleeping. So it's sort of to be determined. I have uneasy feelings about this, but I don't think it's fatal in any way, shape, or form.
Yeah, that's kind of a follow-up question about the shared memory. It sounds really scary. How do you think will we get the memory model right and don't make similar mistakes as happened in Java or C++ before?
OK, memory model questions. Oh, those are beautiful. Well, it all depends on what you mean by right. So my impression of
like not get results out of thin air, basically have well-defined behavior.
Well, I was about to say, the experience with memory models seems to be that we go wrong when we try to do too much. There's someone in the back there. Like, for example, like all the weakly defined atomics that you talk about, results out of thin air. It's because people said intuitively, well, we want writes that don't tear, but we want no ordering constraints. And I think what people have learned is that the ordering constraints are what make memory models work. Is you have to say there's happens before, happens after relationships. So from the memory model perspective, like just being very conservative is you say that we're going to take what C++ calls acquire release and sequential consistency and say that's it for now. Then you have all sorts of ugly questions about what happens when you actually have races and defining those. Because if you say it's totally undefined, then you're like, well, your encryption key suddenly appears on each read. And well, obviously you don't want that. So tightening down a little more and say that, races happen, you get junk, but it's guaranteed to only affect your address space and you won't materialize stuff from outside it, yay. And then there's a question of how do you emulate Java by having non-ordered but non-tearing reads and writes. That's kind of equivalent to the weak memory model. In that case, worst thing you do is you turn all the memory operations into atomics, and Java really sucks when it runs. So that isn't a very satisfying answer there. So like, there has to be some sort of weak memory operations at some point. But right now, we're just punting on that and saying acquire release and sequential consistency only. So sorry to anyone who doesn't know memory models.
You've mentioned the need to read from files a lot. What are your needs, or do you have a concrete set of needs for a future file or file system API, something that I may or may not be giving a lightning talk on later?
It's a good question. This has sort of been a sore point of the web platform in many ways, in part because how do files relate to caching? Right now all the data is ephemeral. And then you have persistent data, and that always tends to be a little awkward, in my opinion. But I think the important thing from the native code perspective is more being able to emulate it and have something that's actually a file. I can pull data from wherever. I could, write a polyfill that goes to IndexedDB or something along those lines, whatever. But the more important thing is that whatever APIs we use for data retrieval, they have to be thread friendly. And they have to be potentially synchronous. But I mean, any sort of persistent data storage would be happy. I realize this is an issue, though. Streaming APIs also, they're sort of happening, and those would be very nice.
So what are your plans to make sure that, like, the web platform as we have it these days, it's inherently asynchronous. We have all kinds of threading models already in the platform. So now you present like some potentially alternative kind of threading. You talk about access to web APIs, DOM APIs from non-main thread. You talk about synchronous access. So what is your plan to make sure that like these plans evolve together with the rest of the web platform, as opposed to just WebASM, even if it's cross-browser, coming up with like this is how we think it should be, and then it clashes with the rest of the web platform?
Well, the first step is give a talk at BlinkOn. So, I mean, all the talking about don't freak out is when I stare at this and I look down the road, I realize that this is a very opinionated and strong statement about what the web platform should be. It's saying that we need compatibility with native code, simply to make porting easier, to make it easier to do the extensible web, things along those lines. But this potentially has impact for everyone working on the APIs. And if we actually succeed, I think we need everyone on the same page. This is like something that we can't just go off and do and then say, ha-ha, because that doesn't make a good platform.
I mean, so like when I hear native and web, what I think is Polymer or something, and not necessarily C++. So it's not entirely clear to me when you say like we need these kinds of APIs.
Yep.
Like who we is. I mean, I saw that some, like you have Unity and those kinds of applications, and we saw a bunch of ASM.js demos earlier, which I guess would be even faster on WebASM.
Yep.
But like, what is the use case you envision? Apart from, because I don't think we will ever run Unity on like an Android 1 device or something.
We'll ever run what?
A Unity game on an Android 1 device, right? Whereas we have like, the Flipkart app launching on top of the existing APIs already now on Android.
Yeah, sorry, having to reboot what we're talking about in terms of use cases and scenarios. I may have to throw that one over to the PM. So like cross-platform development, like when we're talking about Unity, that's essentially what we're talking about, is we're talking about people who have strategic questions and they want to paper as many channels as possible to try to maximize their revenue. So that's one use case we're looking at.
I can help with the use cases if you want, Nick.
So Seth.
Yeah. Hey guys, I'm PMing the WebAssembly project here. I think the first thing we're looking to for use cases is the apps that people are already building with ASM.js using Emscripten. And I think a lot of these use cases are things like well, there's two categories. Let's say there's computationally expensive number crunching, and that tends to come up a lot in games and media decoding and transcoding, and sort of scientific data processing. So I guess what I'm trying to say is we're responding to a need that I think we see through the use of ASM.js today. There is an interesting philosophical question about what the web is, but I think we can just respond to what developers are trying to build today and make that possible.
So I can't necessarily go into details, but on the NACL side, we've had a lot of internal people at Google where they have server-side code. And then they're like, well, we could also run this on the client. And this would have very advantages. We can pre-process it. We can do things along those lines. So it's something that people have been wanting to do for a while, but like all the pieces are not quite there yet. So to some extent, it is speculative. We've had people repeatedly say we want this. We've had people try to do things, but because it hasn't really been there and been solid, it hasn't taken off. So what are the use cases? Yeah, we think they're there. We see they're there.